started section 9.2, excuse me, last time. We're taking a look at multi-stage experiments, and we had seen a couple of them. We've done one where the probabilities changed every time, right? Because we were drawing numbers or names, in this case, out of a hat. We did a tree diagram for this one. We did one over here where we didn't do a tree diagram, but we wrote out all the possible scenarios because they were all equally likely to happen, and so we were able to do that way. This is another one we did where they were all equally likely to happen, even though the stages were a little bit different than the one before. They weren't pulling things out of a hat. And we did one where we saw uneven, like ending pieces of branches and talked about the fact that that's okay, right? So some contexts actually have this kind of a feature going on, and you'll have some in your homework that will too. All right, so we're going to take a look at another example today. This one's a family example. So Joe says if a family has 2 children, the only possibilities are 2 boys, 2 girls, or one of each. Because there are only 3 possibilities, the probability of having 2 boys is 1/3. Is Joe correct? So we're going to draw a tree diagram to explore his thoughts about this and see what it looks like if we follow this line of thinking. So we're having only 2 children. Okay, so the branches are going to represent the individual children being born. And it doesn't even matter if they're twins or if they're one after another. It's completely irrelevant. So we just have the first child, right? So child number 1. So this is child number 1. And the child number 1 is either a boy or a girl. So I'll just use B's and G's since he's talking boys and girls. So what's the percentage or the probability, I should say, that you're going to have a boy if you have a child? 50-50, right? This is a 50-50 chance. So you can either put decimals, I'll do decimals on this one, or you could have done fractions and done 1/2. Either way is fine. This is child number 1. After child number 1, we have child number 2. So child number 2 is drawn as another set of branches off of each of those probabilities, right? Each of those branches that we had from before. And we repeat the process with the B's and the G's. And all of these branches are 50-50. They're all 0.5s, right? So this is a very symmetric looking graph. 50-50 on everything. So let's actually figure out what the probability of having 2 boys is, because that's the one that actually is stated by Joe, is the probability of having 2 boys. So that's this line up here. So if I were to multiply along this tree branch, because that's what we learned about last time, what is the probability of having a boy and a boy? What's 0.5 times 0.5? It is 0.25. Is that the same as 1/3? No. What is it in fraction terms? It's 1/4. So Joe's not right. It's not 1/3. It's 1/4. But why? Let's look at the other part of his statement. He says there's only 3 possibilities: 2 boys, 2 girls, or one of each. So this first branch was boy, boy. And the last branch is girl, girl. And the middle branches are boy, girl, or girl, boy in either order. But I get one of each. So are there really 3 possibilities? Not exactly. I mean, there's 3 different possibilities, but 2 of them duplicate, right? 2 of them are the same thing. At least 2 of them represent the same arrangement of children that we were talking about. So we really have 4 different outcomes if you consider maybe like age order or likelihood of each one individually, those kinds of things, right? So as we're responding to Joe, we have to identify some of that. I'm going to shrink my diagram, and I didn't mean to do that, and then we'll write a response at the bottom. So remember, one of the things I think is a good idea to do when you're working with students is to identify things they did right. I think that's helpful. So there are 3 probabilities. There are 3 outcomes. That's not the space enough for that. Two boys, 2 girls, or one of each. But the boy-girl outcome happens in 2 ways. We can do boy-girl, or we can do girl-boy, right? So So it's really more like there's 4 outcomes, if you consider it that way. It might be easier to not think about the case of twins because it feels a little bit funny, but if you have an older brother and a younger daughter, right? Or you have an older daughter and then the younger brother, those are very different family arrangements. Okay, some of you know exactly what I'm talking about. You're like, oh yeah, I had one of those. Maybe you're the oldest and you are one of those, I don't know. But they're very different family arrangements. So it might be easier to think of it from that perspective. So there are 4 equally likely outcomes. And the probability of 2 boys is 1/4. Or you can do 0.25 if you prefer. Does that make sense? But you can see the confusion? He's treating it almost like it's this problem over here with the spinners, right? Like if this problem with spinners had been such that they weren't equally likely, I couldn't just write them all down this way. The only reason I could write them all down this way is because I had a 50-50 spinner on the left and I had a 1/3, 1/3, 1/3 spinner on the right, right? If those had not been equally distributed, I couldn't have even written them like this. I would have had to draw a tree diagram and put probabilities in for it to even make sense. But he's treating it almost like that. Okay, so the next example that I want to bring to you is actually something very personal. This is my life story, okay? So are any of you familiar with Huntington's disease? Okay, I've got some nods. If you're not, I'm going to tell you a little bit about it. So Huntington's disease runs in my family. Huntington's disease affects your central nervous system. So what it does is that at some given age, depending on a lot of things, we'll talk about in a minute, your brain starts overproducing a chemical. We'll call it a chemical. I'm not sure if that's really the right science term. You can talk to some science person about it later. But you're overproducing a chemical, and this material that gets produced gets in the way of your reflexes happening the way they should. And so the time it takes for your brain to tell your hand to stop the ice cream machine from coming down at a place like McDonald's, if you're working there, it takes too long, and you end up with ice cream all over the plate, that kind of thing. Or the time it takes your brain to tell your foot to stop and to hit the brakes means you're probably going to hit the car in front of you at some point, okay? So it interferes with your ability to do these sort of basic things. Eventually it interferes even with your ability to do things like swallowing, to maintain your balance and so forth like that. Okay, so it's much like other diseases. It's not what kills you, right? It's not, you don't die because you have Huntington's disease. You die because of complications of it thereafter, right? So Huntington's disease runs in my family, and my grandmother had Huntington's disease. My father did too. In fact, my grandmother having it meant that each one of her children had a 50-50 shot of having it. That's the way it works. Kind of like our example with the boys and the girls. It's a 50-50. If your parent has it, you're 50-50 shot of having it. So in 2001, my parents decided to tell my brother, my sister, and I about this. So were you guys even born in 2001? Okay, I don't think so. I was thinking we're beyond that at this point. So 2001, before you were born, my family was small. None of us had children anymore, not anymore, but yet. So my husband and I had been married for 3 years. My sister had been married to her husband for 1 year. My brother was seriously dating the woman that he is now married to. So they were in high school, but they were dating seriously at that point, and so he married her later. And so I have the 2 siblings, and we're going to draw a tree diagram of the possibility of us having Huntington's disease. That's what we're going to draw. So I'm actually the oldest, which means the first set of tree diagram branches is actually representing me. So there's 2 possibilities with Huntington's disease. You either have it or you don't, okay? So it's not like something where, you might have it when you're young and then you grow out of it, like allergies or something like that, or that you get it later. You either have it or you don't. Showing symptoms is another issue, but that's not what we're talking about. We're just talking about whether you have it. So we're going to call these just have and don't. And that first set of branches is myself. The second set of branches is my sister. So she has the same things that I do, right? She has either the possibility of having it, I'm going to abbreviate at this point, or don't. She either has it or she doesn't. And the last one is my brother. So these last set of branches are my brother. And once again, he either has it, we're calling it H, or he doesn't. Okay, and there's an example you're going to do of a genetic disease. Huntington's is a genetic disease in your homework where it's not evenly done. But this one's a 50-50. 50% chance you have it, 50% chance you don't. The example in yours, I think, has to do with either vision or hearing loss. I can't remember. And the values are not equally done. But the process is the same until this point. Okay, you draw the diagram the same way. You just put in the values that they give you. So on this one, all of the values are 1/2. Because I did the last one with decimals, I'm going to do this one with fractions. But if you want to write it in decimals, feel free to write it in decimals instead. So these are all 1/2 probabilities. Okay, so far so good? All right, so the first thing we're going to actually be finding is the probability that at least one of us has Huntington's disease. Okay, so we did a question like this last time. Our question was, what's the probability that at least one male goes on the trip to Hawaii? You remember that one? And what we found out is that if we look at all the branches where at least one person has it, it's almost all of them. Isn't it? Almost all of them. In fact, sorry, I didn't mean to do that. In fact, it's every single one except for the very bottom one, right? Okay. So on the very bottom one, this is the only one that we would not be considering. So there's two ways to do the problem. You can either multiply along all of the other 7 branches and add them up, okay, which is fine. You can do that. Or what you can do instead is you can take 1 minus the probability that none of us does. That's my last branch. And if I do it this way, I only have to calculate 1 branch instead of calculating 7 branches, so it's a quicker process. Now, along that branch, they're all 1/2. So it's 1/2 times 1/2 times 1/2. So what do you get when you multiply 1/2 times 1/2 times 1/2? Somebody switch to bring it 1/8. Yes, it is 1/8. What is 1 minus 1/8? 7/8. Somebody tell me what this is in decimal form, just in case there's others who've done it in decimals. You have it? What is it? You're right. It's 0.875, or 87.5%, right? Almost 90%. We're at almost 90%. So there is almost a 90% chance that at least one of my sister and my brother and I, that one of us will have it. That's really high. And if you added a 4th child to the mix, it would get even higher, right? Every subsequent child would make this a bigger number, that at least one of them would have it. It's the same reason that people kind of think, like, well, if I have a whole bunch of kids, at least at some point I'm going to get that girl. Well, maybe and maybe not. Do you know families that are all one gender, or all girls, or they're all boys? Yeah, I know a family has 6 girls. I think that's what Dad thought. Eventually, he was going to get that boy,
yeah,
right?
My mom, she's named Jerry because she was supposed to be the boy and she wasn't. So her father said,
There you go.
"I'm naming you after me."
At least you're going to get one with the name you've. So that night, when my parents had shared that information, I didn't draw a tree diagram, but I did this calculation in my head. I thought through what the likelihood is. Like, what's the likelihood that Huntington's goes away from my family, knowing what I know about mathematics, basically? And it's not real high, right? There's only a 12.5% chance that we'll all come out of this thing and don't have it. That's not real good. If that were your chance of something happening, you probably wouldn't take that risk, right? Like, that's not real high. And so that night, actually, we'd been married for 3 years. I mentioned my husband and I, and we were actually visiting from out of state because we were living in Kansas at the time. And it was Thanksgiving time. And my husband and I talked, and we made that decision that night that if I had Huntington's disease, we would not be having children. Absolutely refused to move forward. And the reason we refused to move forward was because of this. Because I knew that the likelihood of passing it on to at least one of my children was going to be really, really high. And I was in a position to make that decision on the front end than on the back end. Like, my mom had already had all her kids. She wouldn't have even, looking backwards doesn't make sense in the context, right? We can't look backwards and say, well, if I had made that decision, then I wouldn't have had you kids. So that's what my mom was thinking. And so when my parents knew that that was the decision that we had come to, they didn't like that decision very much. They thought that that was, from their perspective, looking backwards, tragic, because they wouldn't have had their 3 children. But we weren't looking backwards. We were looking forward, and we were saying there's lots of kids that need homes. And this is what we think we're supposed to do if I have it, because I'm not going to purposely push this forward if I can avoid it. So we actually waited 2 years before I went and had genetic testing. So we got married when we were very young. We weren't ready to have kids right away yet anyway. And so we waited 2 more years after this before I went and had my genetic testing to see. It's not a simple genetic test. It's not like they just go take your blood and they just tell you what it is afterwards. They're counting triplet repeats on your DNA. That's how complicated it is. And there's a certain gene called the Huntington's gene. And if your triplet repeat count, A's and T's and G's, and there's another letter, but I don't remember what it is. But if it repeats this certain way, then you will have Huntington's disease. The number is a 44, if I remember right. If it's above a 44, you're going to have it. And if it's below a 35, you don't. And if you're in between there, it means you don't have it, but your child might. So the only time that the numbers change, right, in your children is if you're in the 35 to 44 range, right, that in-between range. So my dad had a number over, or maybe it's over 40, whatever. He had the higher number, which meant that I didn't have to worry about the gray area. It didn't matter. I either would have it or I wouldn't. And if I didn't, then I wasn't passing it on to my kids. Interestingly enough, my aunt is the only other child of my grandmother. My aunt didn't get married till she was 50, and so this also didn't actually come into play for her. But she had the lower number for my grandmother, but the lower number for my grandmother was actually in the gray range as well. So even if she had known all of this from the outset and been able to do all this sort of things, she still would have had the possibility of passing it on to her children, which is just crazy. And there's no history before my grandmother of anybody having it. So it's a genetic mutation, and that happens in our genes. That's the reason the gene pool is what it is, and how when you look at the Old Testament, you're like, well, how could these 2 people, right? Think about Abraham and Sarah. They're related. How could they get married and have kids and their kids not have genetic problems? Well, because we didn't have all the genetic mutations that we have today. That's why. And so hers was a genetic mutation. So we got tested. You have to go through psychological testing. They take you in and they do like a psych eval on you and make sure that if you have it, that you're going to be okay, or sort of, right? Because it has been cases where people find out that they've had it and they kill themselves. Or worse, they kill their children first and then they kill themselves. That's happened too. It's truly tragic. And so through that psychological evaluation, they even talked about, like they asked me, like, well, what if your husband says if you don't have kids, I'm going to divorce you? Or what if your husband says, if you have this disease, then I'm going to leave you? And I said, we don't believe that. Divorce is not an option. And they look at you like you're crazy. They do. They absolutely think you're crazy. And percentage-wise, there's justification for that. Divorce rates in the church are just as high as divorce rates outside the church. It's very tragic. But we had made that decision early on when we got married, that divorce was simply not going to ever be an option. And so we found out I think the whole process took a couple of months maybe. We found out that I don't have Huntington's disease. However, it took 2 years for us before we had made the decision that we were ready to be tested. And in that 2-year time span, God made it very, very clear to us that it didn't matter what the outcome was going to be. Adoption was going to be part of our story. So we went into that knowing that regardless of that outcome, we were going to be adopting. But depending upon that outcome would be whether or not we would have biological children as well. And so not having that disease is the reason that I have my daughter Abigail. So Abigail's the one who's a sophomore speech and theater education major up at MNU. But because we went through all of this is the reason I have my other 7 kids, because God made it clear this is going to be part of your story anyway. So where we are now is that my brother and my sister still haven't been tested. My sister was going to get tested at one point, and then she backed out. And the reason she backed out at that particular point in time was because she was pregnant. And they won't let you test. They won't let you test children under 18. They will let you test in utero. So if she had found out, she would be left trying to decide what to do about the fact that she was pregnant and she wasn't going to abort a child. That wasn't what I mean. But she would have to live the next 18 years knowing that the child might have it because she for sure did, right? And she wasn't willing to go through that. The other thing that they are able to do, and this is actually the reason my parents finally decided to tell us, was because what they can do is that they can do like artificial insemination. So they can take an embryo, they can grow it to 8 cells, it has to be 8 cells big, and they can test the embryo's DNA at 8 cells. So when it's 8 cells big, they can test the embryo, they can tell you whether or not it has Huntington's disease. How crazy is that? It's really crazy. So what people do, there are people who do this, is that they do this, right? They go through all of that, and they test the embryo. And then once they know what the embryo status is, they only implant the embryos that don't have the genetic disease. And in extreme cases, you hear people running children so bad that they want a specific gender, and they do this too, right? Yeah, they only implant the female ones, or they only implant the male ones. So in the process of this is why my parents told us. My husband and I listened to that, and we went, no, I'm not comfortable with that. Even if I felt like, yes, I would only implant the ones that didn't have it, like what do you do with the ones that do? If I believe that birth happens, that life happens at conception, right, at the point when it's formed, what do I do with the ones that have Huntington's disease? And I'm left with no answer. And so we felt like it was too much playing God, and we refused to do it. My brother and sister also refused to do it. They just refused to make any decision at all. That's their choice that they made. My sister now has 3 children. My brother has 2 children. All of them are age 10 and up at this point, the oldest being, he's about to turn 20, so 10 to 20 years of age, the 5 kids. So this next question is actually what it looks like for my sister and my brother's situation now. So I was tested, I don't have it. Given that I don't have it, what's the probability that at least one of them does? So if you take a look at this picture, what's happened is that this picture right here, we've eliminated part of it. We've eliminated this entire top branch because I don't have it, right? And we don't need to test this part anymore either because we know that I don't have it. So the part of this diagram that still applies is the part down here. I'm going to have to delete one piece of this when I get it copy and pasted. No yellow. I'm missing a 1. I think everything else copied. So the first branch is my sister, the second branch is my brother. And if we were to repeat the question that we asked before, right, it was an 87.5% chance that at least one of us had it before. And we want to know what's the percent chance that at least one of us has it now. We can do the same thing. We can simply take off this bottom branch. So we can do 1 minus the bottom branch, which is 1/2 times 1/2. So 1/2 times 1/2, or 1/4, and we subtract it to get 3/4. Or if you wanted to do it in decimal form, you'd have 0.75. So there's still a 75% chance that one of my siblings has this disease. I was going to mention, like, when does it show up? So Huntington's disease is really weird. Its onset is approximately the age of onset of your parent. So my dad's onset was in his 40s. I'm in my 40s now. So it was in his 40s. But the thing is, it's that age of that parent plus or minus 18 years. That's a big span. So my brother and sister are not that much younger than me. My sister's 1.5 years younger than me. My brother's 2 years younger than her. Okay, so they're in their 40s as well. So we're definitely in that range of time that if they're going to have it, they're going to start showing symptoms, but they might not for another 20 years. And it would be perfectly reasonable that they might not for another 20 years. So you can't just tell when you're going to have it show up. It's kind of a crazy thing. But it's a crazy thing in so many ways. So I think that's my last example, isn't it?